Good morning, gentlemen. So last class, we really spent a lot of that time focusing on factor conversions. And with those conversions, we really kind of focused on things that we've been used to. So for example, we could say, if I have 144 donuts, how many dozen would this be? And in this one, we kind of focused on using that train track conversion. So remember, I always would put my given, in this case, my 144 donuts in the top. So I had that right here, and that acted as my givens. And then after that, I would use this to cross-cancel my unit. So because it's given, I want to diagonally cross-cancel, so I'd put my unit that matched my given in the bottom without a conversion, and whatever my target was. And in this case, because my target is dozen, I'm going to put dozen at the top. Once I got my initial setup, I needed to do my conversion, and in this case, we know that 1 dozen is bigger than 1 donut. So I give the 1 to my dozen, and then in 1 dozen, I had 12 donuts. Well, once I solved that, my last step would be to solve. So in this case, my donuts would cancel out. I would multiply across and divide by the bottom. So in this case, I'd be left with 144 divided by 12. And when I calculate that, I'm given 12 dozen. And I need to include my unit. Well, then over your homework, you watched an ed puzzle that introduced the concept of the mole. What's really nice is we can use the mole similar to how we use the dozen, but instead of using it with things we see, these are calculations that we can do in the lab to determine how many grams I might need. So why do we use the number 6.02 times 10 to the 23rd? Well, the big reason we use that is similar to kind of how we have a dozen. The 6.02 times 10 to the 23rd represents a quantity of atoms or molecules in an element or a specific mass number on the periodic table. So when I talk about a mole, I'm saying, there's 6.02 times 10 to the 23rd atoms or molecules that are in that element during that time. It's kind of similar to how I say I have 12 donuts in 1 dozen. What's nice is we can use this number to connect and convert. So if I'm given moles, I can calculate how many grams something might have. So keeping with that idea of molar mass, we can take away our 6.02 times 10 to the 23rd, and instead we can substitute the 1 mole in, so that way we're not dealing with that exponent all the time. Because I can connect them with my periodic table, I'm able to connect the molar mass of 1 mole with an element on my periodic table. And the number I use to kind of equate these together is actually going to be the mass number. So in this case, if I'm looking at my first one, my blue box, I have the mass of 1 mole of an element, like for example, calcium. So if I want to simplify that, I can say 1 mole of calcium by looking at the decimal on my periodic table is equal to 40 grams calcium. I can also turn around and say, 1 mole of copper is equal to 64 grams of copper. And again, I'm just getting these numbers off my periodic table, but I can build off this one step further. If I'm dealing with a compound, for example, then I can also equate the molar mass or the added decimals of that element and set that equal to 1 mole. So for example, if I had 1 mole of calcium chloride, I could say, 1 mole of my CaCl2 is equal to, and I would add those decimals together. I'd still look at my periodic table, and in this case, if I'm looking at calcium, I'd have 40 grams. And then I'm going to add that with 2 times my molar mass of chlorine, which is 2 times 35. If, kind of to help you, I would do 2 times 35, 70, and then I have 40. When I add those together, that's going to give me my mass of 110 grams of CaCl2. We can do the same thing with water, where 1 mole of H2O or water is equal to the molar mass. And in this case, it'd be 16 for the oxygen plus 2 times 1 for the hydrogen to give you 18 grams of H2O. So it's similar to what we did last class where I was taking, quarters to pennies, pounds to ounces, those things, but instead of using things that we might see in our everyday life, we take these numbers for chem and we can apply this in the lab so I can figure out how many grams of a substance I might need. So like I said, where this becomes important is how we use it in our grams. So for example, I could ask you, if I'm in the lab and I weigh out 12 grams, we know we have 1 mole of carbon, right? Let's say, I have 24 grams of carbon. How many moles is that? Well, what I could easily do is I could do a train track or a calculation to solve this. Now I know this one is fairly easy, but it's still important to kind of go through the steps. So if I had 24 grams of carbon, I would still use my train track and I could say, 24 grams of carbon. I want to cross cancel my grams. I want to end in moles, right? And then I look at my conversion. We know in 1 mole of carbon, I have 12 grams. So then once I'm done, I can cross cancel those out. I know I'm going to be left with moles, so I can continue. And just like before, I would multiply across, divide by the bottom. And in this case, I have 24 divided by 12 to give me, 2 moles of carbon. Now, on the flip side of this, I could take this and say, okay, I have 2 moles of carbon. How many grams of carbon would that be? And in this case, I could do the same process I did before. I could say I have 2 moles of carbon. I set up my T. I want to cross cancel moles of carbon and in grams of carbon. We know in 1 mole of carbon there's 12 grams. And then in this case, I would multiply, divide, and I'd have 2 times 12 to give me 24 grams of carbon. Now in this case, some of these numbers will be easy. If I say, I have 24 grams of carbon, you should be able to go, 24 divided by 2, that's 12 grams, so I know that I've got 2 moles. But you might also see numbers where you're dealing with decimals. And being able to do this process is extremely critical to your success, because if you struggle with it, then when we get to the decimals, you might have a hard time. So using this kind of idea, let's say if I'm going moles to mass. So we kind of practiced with this before, but let's see what it looks like when we don't have as easy numbers. So in this case, if I want to know how many grams are in 0.067 moles of carbon, I'm still going to look at my periodic table to kind of help. So in this case, I'm going to set my train track up kind of like how I did before. Oops. I'm going to use my change that color, there we go, 0.067 moles of carbon. And I want to cross cancel my carbon, so I'm going to put moles of carbon on the bottom, grams of carbon on the top, and I still use that same conversion I did before. I'm going to look at my periodic table, and to make things easier, round it to a whole number. I know that in 1 mole of carbon, based on this, my mass number, I have 12 grams of carbon. So then to solve, I am going to take 0.067 times 12. So when I do that in my calculator, I'm going to be left with 0.804 grams of carbon. So in the lab, for example, if I wanted to get 0.067 moles, I would need to mass out 0.804 grams of carbon. And just like above, I can also use grams to moles conversions if I'm curious how many moles I have in the lab. So just like before, I'm going to follow the same process. I do 78 grams of carbon. Grams of carbon goes on the bottom, moles of carbon on the top. I know that my 1 mole is always bigger. I look at my mass number. I know that's 12. My grams will cancel. And to solve, I would do 78 divided by 12. And when I divide these are going to give me the amount of moles. And in this case, I'm given 6.5 moles of carbon if I had 78 grams. Now, we aren't always going to see conversions from mass to moles. Sometimes you may have to use the scientific notation number of 6.02 if I'm asking for atoms or molecules. So let's see what that could look like. So, like I said before, we might have moles going to atoms. So in this case, the mole conversions I'm going to use is my 1 mole is equal to my 6.02 times 10 to the 23rd. And this could be atoms, molecules, and anything really. We're still going to use our train track, but instead of using our periodic table, we are now going to have to use our number here. So for example, I could ask you how many atoms are in 2.12 moles of lead. You're still going to follow that same process we did before. So you have your 2.12 moles of lead. But instead of using that molar mass, because I'm going to cancel, I'm going to use, because I want atoms, my 6.02 times 10 to the 23rd, not 24, excuse me. So I'm going to set this where my moles are on the bottom. And in my atoms, I have my 6.02 times 10 to the 23rd. My moles cancel out. And I'm going to multiply my 2.12 times 6.02 times 10 to the 23rd. Now, when you calculate this, remember, you want to put it in your calculator a little bit specifically. Based on what you have, remember, you're going to utilize the EE button. So if this is typed into your calculator, you're going to do 6.02. And remember, if you have a green calculator, you're going to use that EE function. If you have like the Texas Instruments, you're going to have to hit the second EE. You're going to have an E populate, and then you're going to have to type 23, and that's how you're going to put that in your calculator. Now, when I multiply these together, I do 2.12 times my 6.02 EE23, and I will be left with 1.28 times 10 to the 24th atoms of lead. Now, you really won't use this calculation a whole lot when you're doing things in the lab, but it is important. It's an important skill to know. So let's see what happens if I had to go the other way and go from atoms or molecules to moles. All right, so here I'm asked how many moles of magnesium do you have if you have 1.25 times 10 to the 23rd atoms of magnesium. So like I said before, we're not going to be using our periodic table. Instead, we're going to use the conversion I have here. And that's where I'm going to use my 6.02 times 10 to the 23rd. So it's still kind of following that same process. In the beginning, I'm giving 1.25 times 10 to the 23rd atom. So I'm going to write that down like I would usually. The only difference is now I'm going to have to go from atoms to moles. So I know that I have 1 mole on top. I need to have atoms on the bottom. And that is where I'm going to type my 6.02 times 10 to the 23 atoms. To solve, just like before, I'm going to multiply across, divide by the bottom. So in your calculator, you would do 1.25 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. But what's nice, and if you kind of notice, my exponents match. So instead of typing them with my second EE button, I can cancel those out and just do 1.25 divided by 6.02. When I do that in my calculator, I'm given an answer of 0.208 moles. What's nice about doing it that way is that you don't have to worry about as many errors, because sometimes you might type in your 10 to the 23rd incorrectly. So if it's the same, you can cancel it out just by doing your simple math, because exponents divided by each other are subtracted. So this is kind of the general gist, but what we're going to kind of expand on is what is called a mole map, and you will see that in the Ed puzzle. The mole map will grow as we progress, but what is really nice about this is your focus today is really going to be going from grams to moles and moles to grams. When you do this, the arrow is going to signify how you are going to set up your T. So for example, if I'm going from grams to moles, I would follow this arrow here. And when I do that, if I went from grams to moles, I would have to have grams cross cancel, and I'd be ending with moles. So it kind of shows you, hey, this is how you're setting up your T on this side. The same process is going to carry over when you go from moles to grams. So while I follow that arrow, I would have, my moles on the top. My moles would cross cancel. I'd be left with the grams on the top. So I have what my train track is going to look. What is nice is that as you grow comfortable with using this map and as it grows, you might not have to worry about cross-canceling your units as much, but it is still important to set up your T as it is critical for your success. So what you are going to do today, if you have not started already, is you are going to work on the lab activity. You're going to have some different numbers than what other people in your class might have, but I want you to try and see how going from grams to moles, moles to grams looks like, especially with a visual in the lab. If you have any questions, let me know, but hopefully this will be very critical for your success.